Hello viewers, welcome back to the course on matrix computation and application. So, today we are going to define some other terms related to the linear transformation. So, let us do that one. So, now we are able to know that suppose we have a linear transformation from a vector space U to a vector space V, then we in the previous lecture we have discussed that how we can find the linear transformation from U to V that is uniquely determined. Now, today we are going to define some other terms related to the linear transformation, and that is called the range. So, range of T, and that is represented by R of T. So, that these things we have already discussed when we discussed about the linear map from Rn to Rm. So, now we know that what is the range space of T. So, range space of T is a set of all images under the linear transformation T. So, I can define that the RT is a set of all T belongs to U such that U belongs to the vector space U. Another thing I want to define is the null space or kernel of the null space or anti. Not the null space, we just call it anti, and I call it kernel of T. So, this is a set of anti, we represent by anti, and this is set of all U belongs to U such that T of U maps to 0 element of V. And from the previous knowledge we also know that, so this is equal to rank called the rank of T. So, it is represented as rank of T, and this is equal to nullity of T. So, that things we have already discussed when we have defined the matrices from A from Rn to Rm. So, in that case we have already defined what is the rank of the matrix, what is the nullity of the corresponding matrix. So, the same way we can define everything, that rank of T and nullity of T. Also, I know that the range of T is a subspace of V, and also NT is a subspace of U. So, these things we have already discussed, that now we have a linear transformation that is my U to some V, and we are defining the linear transformation T. So, this is my U and basically this is my T of U. So, from here I can define T. So, my RT will lie here somewhere, and my NT, the null space or the null the kernel of that the transformation T. So, that will be belongs to the subspace U. So, these things we have already proved that these are the subspaces of U and this is the subspace of V. So, this is what we have already done. Now, also we can define whether, or we can define or we can check whether T is 1 to 1, that is injective, and on to, that is surjective. surjective. So, this is also we can check. So, and we also know that how to check for the 1 1. 1 1 means how to check this one. So, for this one we will say that the transformation T is said to be 1 1 or injective if T of x 1, suppose I take, is equal to T of x 2, that implies my x 1 should be equal to x 2. This is the one of the way. Or for any x 1 not equal to x 2, that will implies that T of x 1 should not be equal to T of x 2. So, either this way or this way. So, these two conditions, either of the condition I need to satisfy to check whether this is 1 1 or not. The second one is onto. So, for onto, if the range space of T is equal to V, then T is called onto. So, this if I take the range space of T and that is equal to the vector space V, because we are defining T from U to V, and if my range space is equal to V, it means that for any element there is a pre-image in U such that T U is equal to V. So, that is called the T onto. So, how to check? Now, we can say that T is said to be onto if for any element V belongs to V, there exists some element, or I can say there exists at least one element, say U belongs to U, such that T of U will be equal to V. So, if that is true, then we say that this linear transformation T is onto. So, this is the few definition we have defined. Now, I want to check that how we can find this range space and null space when a transformation is given to us. So, let us do one example, because we already know that if we have a map A from Rn to Rm, so in that case we know that how to find Rt. So, if you remember, then my matrix will be A, so that will be n cross m. So, in this case, because I need A x is equal to B. So, x is coming from n, so it is n cross 1. So, it should be m cross n, and that should be m cross 1. So, the matrix will be m cross n. Now, if you remember, then we know that the range space of A is spanned by the columns corresponding to pivot elements. So, the columns which has the pivot elements, so we take the corresponding columns in the given matrix. So, that will span the range space of A. So, this way we can define, and also we can define the null space. We take the matrix A into the echelon form A into the echelon form U, and then the 0 rows corresponding to the 0 rows, that rows span the null space, the n of the given matrix A. So, that is the way we can define these two things. Now, let us take one example. I have a linear transformation T from suppose V3 to V3, and this is given to me as T of x1, x2, x3 is given as, maybe I will just take x1, x2 and 0. So, this is just the projection, because I am projecting the V3 whole space into the plane x1 and x2 plane. Means I have a element, suppose I take space V3 space. So, this is my, maybe I can call it x1, x2 and x3. So, this is my xyz plane, like a xyz plane 3D. Now, in this case I choose any vector element from here. So, that is x1, x2, x3, and I just take the projection on the xy plane, and this element will be x1, x2 and third coordinate will be 0. So, this is called the projection. So, this is the projection transformation. So, this is a linear transformation we already know. Now, from here I want to find the, so I want to find what is the range space of T. So, if you see from here, the range space of T is set of all the elements x1, x2, 0, such that T of x1, x2, x3, that is x1, x2, 0. It means in this case my range space will completely the xy plane. So, here it is very easily I can define that this is equal to my x1, x2 plane in V3. So, that will be my whole range space, because if you see for any value of x1, x2, x3, it maps the same elements except the x3, that will be 0. So, it is the whole, so in this case I can say that this is the plane in x1, x2 plane in V3. So, that is my range space, and also I can say that the rank of this will be 2, because it is x1, x2 plane and which is of dimension 2. So, its rank will be 2. Now, I can define what about the kernel of T, the NT, that is the kernel of T. So, this will be, I want the set of elements x1, x2, x3 such that T of x1, x2, x3 that is equal to 0 element. So, 0, 0, 0, because it is moving from V3 to V3. So, which implies that I want the elements. So, now T of x1, x2, x3 that is given to me, that this is equal to x1, x2, 0, and that should be equal to 0, 0, 0. So, from here I will get that my x1 should be 0, my x2 should be 0, and third edge element is 0, 0. So, I will get only two conditions from this one. So, from here I can write that my, in this case I can define my kernel of T as set of all the elements, that is 0, 0, x3, such that if I define T 0, 0, x3, that will be 0, 0, 0. It means that this is made up of this element. So, from here I can say that, and I know that the basis for this will be 0 0 1. So, I can say that the span of this 0 0 1 vector, that will span the whole kernel of T, and from here I can define that the nullity of T, that is 1 in this case. So, I can from here I can check that my range space is this one and rank is 2 and the nullity is 1, and also we know that rank plus nullity, that is 2 plus 1 3 is equal to the dimension of U. So, here it is coming. I have not proved this theorem yet, the rank nullity theorem, but that is there. So, we will continue, we will prove in the coming lectures. So, from here I can say that this is my rank plus nullity, and that is coming 3 in this case. Now, I want to check whether it is this T is 1 1 or on to or not. So, this one I want to check. Now, from here if you see that since the range space T is of dimension 2 as rank of T is 2 in this case, and the transformation we have taken from V3 to V3. So, which implies that my range space, because that is a subspace of V3, is not equal to V3 in this case. It means there are few elements in V3 which is not coming in the range space of the given linear transformation T. So, from here I can say that my transformation T is not onto, because it is there are few elements in the V3 which does not have the pre-image in U, because my range space is just only this element. So, from here I can say that my T is not onto. Also, I know that T of 0 0 element, that is going to 0 0 0, that we already know, property of T, that is already there. So, it is a property of the linear transformation, but I can define the T of 0 0 1. So, that because it is coming under the null space. So, that is also 0 0. So, that is also coming 0 0. It means, which implies that if I take the mapping, so you can check from there that suppose this is my V3 and another is my V3. So, two elements are there, that is 0 0 0 and 0 0 1. So, they maps to the same element, that is 0 0 element. And so, from here I can say that T is not 1 to 1. So, T is not 1 to 1 in this case. So, from here directly I can check that T is not 1 1. So, this way we can find out whether this linear transformation is 1 1 onto, and then we can define its range and null space. So, let us take one more example. In this case, suppose I define a linear transformation T from V3 to V2, and I define my transformation as x1, x2, x3 is equal to x1 minus x2 and x1 plus x3. So, this is what we have defined. Now, I want to check, find range space of T, kernel of T, and check whether 1 1 or on to. So, these things we need to check for this linear transformation. So, it is already we know that it is a linear transformation. Now, how I can define the range space? So, range space in this case, if you see that the range space, if you find out the range space of T is set of all elements of the form x 1 minus x 2 and x 1 plus x 3, and that belongs to my V 2. So, it is coming all the elements of this form. Now, so this is the way my range is coming. So, range will contain this type of element. Also, kernel of T will give you the set of elements. So, that is the set of elements x 1, x 2, x 3 in this case, such that T of x 1, x 2, x 3 is 0. So, this one is there. Now, it means from here that I want, which implies that my x 1 minus x 2 and x 1 plus x 3, this element should be 0 0. And if you from here I can say that my x 1 should be x 2 and my x 1 should be minus x 3. So, from here I can define, so I can define my elements x 1, x 2, x 3 as, so let us define this one maps to this one. So, suppose x 1 is there. So, my x 2 I can write as x 1. So, it will be x 1 and this will be minus x 1. So, I can say from here that the kernel of T will contain the elements x 1, x 1 minus x 1, such that my x 1 belongs to the field R, that is real line in this case. So, also, so from here I can check that T of x 1 minus x 1 will be, so x 1 minus x 2 it will be 0 and x 1 plus x 3, x 1 plus x 3 that will be 0. So, that is going to 0. So, from here we can say that this is in this form, or I can say that x 1 and this is 1 1 minus 1. So, from here I can say that this vector 1 1 minus 1, it spans the whole kernel of T, and from here I can say that the nullity of T is 1. So, this way we are able to define the range space and nullity. The rank will be, of course, it will be 2, because here it is all the element of this form. Now, the question is that I want to check whether it will be 1 1 on 2 or not. Now, from here, now to check onto, that how we can check the onto. Now, onto means for any element Suppose I take the element, I call it AB belongs to V2, which implies that x1 minus x2 and x1 plus x3 should be equal to some AB, because I had just taken one element AB from V2 and the element of V2 are of this form. Now, from here I get my x1 minus x2 is equal to A and x1 plus x3 is equal to B. Now, from here I can define from here that I can define my x2 is equal to x1 minus A, x1 minus A, and from here I can define my x3 is equal to B minus x1. So, I have written everything in terms of x1 only. So, from here x2 is coming x1 minus A and x3 is coming B minus x1. Now, from here I can write that for t, so I write my x1 and x2 I write x1 minus A and x3 I write B minus x1, I will get my value AB. It means for any vector belongs to V2, there is a vector in V3 such that t of that vector is equal to this one. Okay. So, it implies that for any vector AB belongs to V2, there exists a vector, at least one vector, that is x1 minus A, B minus x1 belongs to V3 such that t of x1 minus A and B minus x1, that becomes AB. Now, you can choose any element from here. For example, you say that I take A is equal to 1 and B is equal to 1. So, what is going to happen in this case? So, in this case x1 minus 1 and 1 minus x1, that will going to 1 1. Now, I can choose my value of x1. So, let I take x1 is equal to maybe 0. So, it will, what will happen? It will 0 minus 1 and 1, that will be 1 1. I take x1 is equal to 1, let x1 is equal to 1. So, t of, in this case it will be 1 0 0, that will go to 1 1. So, from here you can check that for any element in this case I am able to get at least one element that maps in this. So, from here we can say that, which implies that T is onto. So, T is onto in this case. So, which implies that the range space of T is whole V2, and which gives that rank of T is 2. Also, so that is 1 2. Also, the null space, also the nullity of T is 1. So, which implies if the nullity is 1, from here I can say that if you see from here, the nullity is coming from 1 1 minus 1. So, you can check from here that element 1 1 minus 1, that is mapping to 0 0 element, and also we know that the 0 0 0 element will map to 0 0 0 element. That is the property of the linear transformation. So, it means that two different elements mapping to the same element in this case. So, from here I can say that T is not 1 to 1. So, T is onto, but not 1 to 1. So, from here you can check this one, and also rank plus nullity, that is 2 plus 1, and that is equal to 3, and that is equal to the dimension of. So, if you see from here, we are defining the linear map from V3 to V2. So, it is equal to the dimension of V3. So, there is some relation coming up about the rank and the nullity and the dimension of the space U, from where we are defining this linear transformation. So, this way we can define the how we can find out whether the linear transformation is 1 1 on 2, or I can define the range space and the nullity of the given transformation. So, this way we can define. So, let me stop here today. So, today's lecture we have discussed about the range space of related to the given transformation and the null space, the kernel of the given transformation T, and then also how we can check whether the given transformation is a 1 1 or onto or not, and we have discussed a few examples based on this one. So, in the next lecture we will continue with this one. So, thanks for watching and thanks very much.